Let's discuss the data. First, we have some raw data. We have the magnet specifications, the gap specifications. We have the data of what we'd expect from a typical Faraday motor of the same size, and we have the raw steel data. All right. For the solid steel bar, it took 513 grams on a 20 millimeter moment arm to produce 1 Newton meter of force. That corresponds to 197 newtons of force, which would come from 0.8 Tesla's B field. Those numbers are all very consistent with the magnet data and the gap data. We can see for our 20 millimeter generator and our 40 millimeter generator, we consistently had torques greater than the torque from the solid steel bar. Those increases in torque could come from shear forces of 19.72 newtons and 16.72 newtons, which would produce 6 degrees and 5 degrees of vector change from the magnet. These shear forces, you can see, are 100 times greater than what we'd expect from a Faraday motor. Let's look at some of the compiled data. All right. We also have data with no separation or no offset of the magnet. All right. These numbers too are consistently compared to the 1 Newton meter and the forces we get from the solid steel bar. These numbers are all very, very large. The torque is large and the shear forces are large. The shear forces are 2 orders of magnitude greater than what we'd expect from a Faraday motor of the same size. So our conclusions. This test data indicates forces exceeding 100 times the force in a typical motor are achievable. We have already achieved double this ratio, but acknowledge that only a portion of the net torque has potency, and the balance is catalytic in nature. This attribute is the secret to free energy. Torque is a scalar quantity which may be nullified or equally opposed. In our experiments, the sum of the potent torque and the catalytic torque are opposed by torque from the overhanging weight. In a motor, the catalytic torque is nullified by virtue of radial force vectors, and the potent torque is opposed by the sum of angular acceleration and mechanical work. For the 20 millimeter reaction bar, the potent torque to catalytic torque ratio is 1.38 to 1, determined from calculations in the prior art. Actual potent forces and CFF ratios in the raw data are therefore only 58% of the listed values, with correlation better than plus or minus 11% in all of our experiments. What does it mean? A 10 kW free energy magnet motor will be no larger than a stack of dinner plates and require less than a quarter kilogram of permanent magnets. The specific power will exceed automotive requirements and may even meet the requirement for flight. And forward. SYNCOPETRA now must deal with the enigma that its goal is royalties rather than manufacturing profits. Someone must risk the cost of building a factory before royalties can be established. It's both a chicken-egg thing and a Columbus-Isabella thing. Columbus and the Queen argued for 2 years before an agreement was reached determining Columbus's fair share. The technical stuff was long resolved by sailors who knew that longitude proved the Earth was a sphere, and Isabella's scientists who could not dispute the simple flat facts. We have turned down an offer of $200K to fund a working generator in favor of searching for an investor with foresight to build a factory capable of producing 1 million 10 kW motors per year, which represents $13 billion in sales with at least $6 billion in gross profit. The tooling requirements for such a factory are estimated at $40 million. Fair share might be determined by a 200 to 300% annual ROI on the tooling investment after scientists are given a chance to dispute the simple facts disclosed here. We have sufficient funds to meet any requirement of proof with a working model, but we won't spend the money foolishly just to satisfy ignorant curiosity. In effect, we are Columbus approaching Isabella after already having made a secret voyage. And we have a dream. Maybe we will live long enough to hear an innocent child ask, "What's a gas station?" But you don't want to hear about our dreams, you want to hear about our discovery. So let's get to them. Our first discovery can be validated with this test fixture. The electromagnets have asymmetric flux density at the poles, but Tom Bearden says they're skewed rather than asymmetric. Regardless, when energized, the pole faces will cog to the position shown. Integrating the shear force and work of passing magnets will be non-zero, biased in the direction of aligned pole faces. Furthermore, doubling the gap between magnets will have a very small effect on the integrated value. I doubt that this could be confirmed with computer modeling. It proves significant amounts of free energy are available. It's a conundrum. We have to choose between believing our crude data or the pretty cartoons from a high-power computer. Shear forces from vector changes are opposed by altering the flux density. It must be refraction, and in a Newtonian sense, it is not exactly equal. Reducing the refraction angle lowers refraction potential energy, while increasing the angle increases energy. It seems analogous to the refraction rainbow effect, where shorter wavelength, higher frequency, higher energy light refracts less. In the optics world, these energy implications are easily avoided by accusing glass of having a variable index. We could make up a similar story for magnetics, but I could not tell the story with a straight face. Our second discovery allows us to isolate the net shear force from the cogging forces. We can't prove this yet, but our maximum forces are getting closer every day to the maximum net integrated force from the passing asymmetric magnets. Accurate computer modeling would help. For a while, our second discovery must remain proprietary. The secret would be apparent if modeling could predict the ideal shapes for a direction compass and for perfect iron filings. It seems the best direction compass would be rectangular with two poles and two side boundaries. Instead, the shape has been empirically established and has no side boundaries. The empirical shape looks like side-by-side triangular prisms to me. I think the empirically determined shape of a pair of iron filings might be very similar. For a pair of filings, I expect the best shape would be mirrored triangular prisms that gravitate to a critical separation when placed near a magnet pole. But we need to define best, and that's easy. We want lots of torque from small angular displacement. Hopefully, that's what we've demonstrated we can do. Torque is the only requirement for rotational mechanical work, and some torque doesn't require energy. Non-Newtonian magnetic refraction might produce that kind of torque.